So let's see. And that's the things. And then we are going to get the V transpose inverse on the both sides. So I'm going to multiply the V transpose inverse on the left to the left here, and then to the left here, and then I got the AV, and then equals to the V transpose inverse. And now I'm going to multiply another thing is the V inverse to the right, and for the both sides. And I got A, and then V transpose inverse, and then V inverse. And let's see the V transpose inverse here. The V transpose is just the lower left matrix. And then if you take the inverse, and then you can actually prove this. The lower left matrix is inverse is still a lower left matrix. But here, this is the upper right matrix. And then the upper right matrix inverse is still a upper right matrix. So now we have, let's see, this is, which is, so this whole thing is lower left, and then this one is upper right. This is the upper right triangles matrix, and which is LU factorizations of the A. And this is a fun fact to know. LU factorizations of A. Any questions here? Is about the A autonomous vectors. Next things I'm going to measure one examples about the conjugate gradient descent. So, no questions, right? Okay, good. So, since if we have such an A autonomous vectors, or a lot of time we just use A orthogonals because it's easier to find A orthogonals methods than the A autonomous. We don't need to do the normalizations process there. So here, there's one theorems about these things, and then it is about the conjugate gradient methods. And these are the theorems 732s on your textbooks, the first textbooks. It's talking about how many steps we can achieve with how many steps we can achieve the exact solutions. And here we have, okay, so we just talk about the A orthogonals vectors. And so let the V1 and V2 and the Vn Bn A orthogonals vectors, A orthogonal set of the non-zero vectors. And then it's associated with this positive definite matrix. And let the x0 be the arbitrary. So I just mentioned the last time, so you can choose your initial vectors arbitrarily. And if we define the iterations, looks like this. So we have the TK, and if you recall what we have done last time, and then this is the uttermost T values to get the minimum values on that directions. And the XK1 is just the k minus 1's iterations results, and the vk, and then a vk. And then this vk here is defined with that a orthonormal vectors, and it's already decided there. And we are going to get the xk iterations looks like this. We are getting the xk based on the xk minus 1, and then with the tk value and that search directions vk, and we call this one is the search directions. So this is the search step size, and then this is the search direction, and then the search directions is just given by that a orthogonal set of the vectors. So this is the algorithm. So we have the TK. This is the simplified versions of the conjugate gradient vectors. And then this is the VK TK value. And then this is how we design their current iterations with cells XK based on the previous steps of the cell and the search step and search directions. So with this iterations process, and actually we can, so we do the iterations k equals to 1, 2, and then to the end. This is just the algorithm, and then the conclusion is that then this is the conclusions. Assuming that we don't have any rounding off, rounding down there in the calculation. But actually in the computer, it was doing some rounding up and then rounding down. But assuming that we have some exact arithmetic here, we don't have any rounding here, and then we get AXN equals to B, which means that at the end steps, you get the solutions to the linear system of the equations. So in the let me see. In the Gaussian-Seidel method, in the SO method, those iterations methods, it takes so many steps. It just you take over n steps. N steps if you have an n-dimensional problem, and then you have over n steps to complete the iterations. But here, you just need at most n step, and then you can arrive the exact solutions to the AX equals to B. So this is the solutions of the AX equals to B. And then this is the results from the n iterations. Any questions? This is this theorem about all the things about this theorem. So with these iterations, and then at the end steps, you would get the exact solution, assuming that you have exact arithmetic, which means that we don't have any rounding here. Any question about it?
So if the rank of A is the low rank, so there's no solution to that.
Yeah, so here we just assume that this is positive definite.
So the rank is common. So
yeah. Oh, you mean this one? But here we're just assuming that we are dealing with that, yeah, and my end is positive. I'm going to skip the proof at this moment, but we will go back to here to prove the theorem because this theorem is quite interesting and quite long. Okay, so let's take a look at one example there first, and then that's something related to your something related to your homework. And then where do I put that picture? So bad. I removed that pictures. Never mind. I would do some quick paste, copy and paste here. So I need to briefly mention that examples really quick, because you need to do the homework. Yeah. So let's see, there's one example here. It's actually on your textbook, and then it's the example example 1 on your textbook. Let me just do the copy and paste here. So if you take a look at the textbooks, and then just the example 1, and then that example 1 tells you something during the pace. Okay. Okay, this is the example 1 on your textbook. There is a lot of information on your textbook, so if you have time, and then you can read it. So let's take a look at the example 1. And so the exact solution looks like this, and then we are going to use the procedures described in the 7.32, and then with the initial guess to produce the exact solutions of the 3 iterations. And here, on this textbook, the V vectors, that is the 8 orthogonal vectors, are given. But now you already know, so we include some information that is not in this textbook. I tell you how to get that V vectors, right? During the Gram-Schmidt vectors process. And then so if you take a look at these vectors, and then you actually can get this vectors by the Gram-Schmidt process, but without the normalizations. So here, let this to be the 8 orthonormal process here, vectors here. You can double check if they are 8 orthonormals, and then just using the A inner product. It's actually the A inner product, checking the V1 and the V2, they are, the inner product is 0, and then V1, V3 are 0, and then V2, V3 are 0, the inner products. And then so this is an 8 orthogonal set. And now we are going to follow the iteration in actually this one is the 732. There are a lot of typos in this textbook as well. And let's see, but less than my typos. I have more typos than the books. So if we follow that that A32's algorithms, you will see that the first things we are going to do. So let me just write down that values again, and then to see what we have here. So in that, so this is the residue. And then VK, and then AVK. And the XK is just the XK minus 1, and then plus the TK VK. So if you take a look at here, the first thing is going to calculate the residue. If we define this as the residue RK minus 1, and then it will calculate these numbers one by one. So it at very first is going to calculate the residue, and then with the residue, it's going to calculate the numerators in the TK. And with the numerator, and then here this is the denominator. So we get the T0, and then that is just the numerator divided by the denominator here. Do we see it? Okay. So 24 divided by 4 is 6. And with all the values here, the TK here, and then we can calculate the X1. The X1 is just equals to X0, and then plus the T0, and then V1. And then the V1 is just given by there, and that's the 8 orthogonal set. And so that's how we do one iteration. And then for the second iteration, so we would do the similar things. And the first things, we are going to calculate the residue. And then the residue is just a B minus A X1, and then this is the residue 1. And the T1, once again, it should be the numerator, and then divided by the denominator here. And then calculate all the things, and then you will do this one by one. And then this is the second iteration. And here we have the third iteration. Once again, we are going to calculate the residue first. This is the third iterations, and let's see. And if you take a look at the third iterations, we get the result, and then that is a 3, 4, -5. And if you compare to the exact result here, it's actually the same result. So which means that we can arrive at exact solutions at the third step with 3 iterations. So that's what the theorem means. The theorem 7.3, 7.32. So it's just saying that we can arrive these solutions at the end step. This is the A matrix, is the n by n matrix, and then we can arrive the exact solutions at the n steps, or less than n steps. Sometimes you just need less than n steps. Let me see. There's one more thing on your homework, and then I need to mention this today, and then I will leave the proof later on because there's just 4 minutes. 3 minutes now. Okay, hurry. I need to mention something on your homework first. So it's about the preconditioning of your let's see. Okay, it's about the preconditioning. So instead of showing the AX equals to B, and then a lot of time the matrix is not very good, and then you were doing some preconditioning. I just briefly mentioned this in today's class because we haven't read a lot of calculation just now. So the preconditioning means that, so instead of showing the AX equals to B, I would just briefly mention this in this class because this is related to your homework 2C, I believe. So instead of doing this, calculating the AX equal to B and then apply the conjugate gradients methods to this matrix, and actually we want a better system of linear equations, and then but it's equivalent to this one. And what we are going to do is to multiply the A by, so we are going to change the A to the A tilde, and then the A tilde is just the C inverse and then times the A, and then C inverse and then transpose. Why do we do this? And then we are going to multiply one specific matrix here. This is C inverse, and then this is C inverse transpose. And then this is because we multiply this one here and then multiply the transpose here. And then this is because we want to maintain the property of the A, the positive definite. If you try to prove this, try to do some proof, and then you find out that this is still a positive definite matrix. So that's why we are going to multiply this. And then a C matrix here is carefully chosen, and it should be a non-singular one because you are going to take the inverse. If we take the A tilde looks like this, and then you would get the new systems, and the new systems looks like this, and it's just the A tilde and then X tilde equals to the B tilde, and then the X tilde here is just equals to the C transpose and then X, and then the B is the B tilde here is just equals to C inverse B. This is because if you take a look at here, if you expand out these things, and then it's quite equivalent to that that AX equals to B. And if I just expand this out, and then it's just the C inverse A, and then C inverse, and then transpose, and then C transpose X. And then this is the A tilde, and then this is the X tilde. And because the C inverse here, the C inverse transpose is equals to the C transpose inverse, and then so we get the C inverse A, and then C, the things is just getting the things in between. It's just this one times this one is just the identity matrix, and then I got this, and this is the C inverse AX, And then on the right hand side, you get the C inverse B, right? So this means that this equals to C inverse B. So you will see the equivalent here, C inverse B, and then if you multiply both sides by the C, and then you will get back to the original matrix, the original linear systems. So, but here, if you compare to, next time I'm going to talk about the benefits of doing such as this, but you need to choose the C matrix very carefully. But in your homework, the homework is actually picking the matrix for you. It's the diagonal matrix, right? And then you will try out that on your homework. And I just briefly mentioned this so that you can do your homework for this 4 days. And so see you next time on Wednesday. And then I will talk more about the preconditional things, show you some examples here. And then shall we skip the proof of the 732? If you want to skip it, then raise your hand. And then if you want to listen to the to know about the proof, and then just put down your hands. Okay. Skip if you want to skip the proof, and then raise your hand. Okay, it's more than the 1/2 of the class. So I'm going to skip the proof, and then if you are interested in the proof, and then you can go back to take a look at the proof, and then you can discuss the proof with me during my office hours. If I'm not going to talk about the proof, and that would not be on any exams, okay?
I wanted to ask, don't we get here how we can do this summation up to like J, I? Yes,
This is more than I.
okay, so it only goes up to I? If wherever I know.
Yeah, this is more than I.
Okay. So what for the first?
So for example, this is 2, right? If we are going to calculate the
Yes.
V2, and then it's just summations with 1.
Yeah, but what about the first one then?
The
J
first
goes
one
up to,
0, so that's
oh,
nothing.
so it's not left, it's just less.
Yeah, less than.
Oh, I see. Okay, thank you.
Yeah.
I have a question. So you said that. So you said that in the problem, the C inverse will be given to us, and we have to choose it carefully. But here it's given to us, and it's equal to the diagonal matrix.
Yeah.
What is this negative
1/2.
Yeah. What
So here you could just see the D 1/2, and then this is just like the diagonal matrix, right? D4 and then 16, right? Yeah. And then D inverse negative 1/2 is just like. Do you remember what's the definition of this one? If you go to the number. It's just the rest of it.
Yeah, 1
and then
over
1/2, right?
Oh, so 1.
Right.
Oh, okay. So this is 1, this is 1/2. This is 1/2.
Yeah, and then this is just like
Got it.
taking the negative 1/2.
Where is the diagonal matrix coming from? Like, where is the diagonal matrix given to us?
So you take a look at the system of the matrix, and that's you take the diagonal.
Of this right here.
Yeah, you have the 1 and then 1/3, and then taking the negative 1/2.
Oh, okay. So we're taking the diagonal of this right here. Yeah. Okay, I understand. Thank you.
I still do not understand like what the 2B's means. It's like you should use the conjugates. It's like codings from the last lecture.
Yes, conjugate gradient methods. I haven't mentioned the whole algorithms. I just briefly mentioned that